All right, so section 2.1 is all about angles, not angels. That would be your religion class that you had earlier today, or maybe tomorrow. I don't know what your schedule looks like. This is a joke because angles and angels are pretty close to spelled the same. Anyways, that was tempting. I didn't even get a guffaw from anyone. So we'll start by defining what a radian is. So if you remember from your geometry class, one unit of measurement that we used to measure angles was the degree, and a second measure was the radian. Most of us probably remember that word, but maybe we didn't get a thorough definition of what a radian is. So a radian, we'll say a central angle has a measure of 1 radian if it intercepts an arc with the same length as the radius. So there's probably a couple of phrases or terms in here that we should probably review because they were things from geometry and it's been a couple of years. So when we say a central angle, what we're referring to is an angle whose vertex is at the center of some circle. So for example, here the angle CAB is a central angle. And it says intercepts an arc. So an arc is just a fraction of a circle. So right here our arc is CB. And we can see that the angle CAB intersects that arc. Everybody's okay with that? We say intercepts when like both parts of it hit it. So we would say that the measure of angle CAB equals 1 radian if and only if AC is congruent to the arc length CB. So this is equivalent to that statement right there. It's just the symbolic version of it. Is everybody okay? I think I hit all the main vocab and ideas in there that were from geometry that might have needed a little brush up on. Again, if I forget something or I don't mention something or I assume something's obvious that you're like, I don't know what that is, again, stop me and holler. Josh? What's in the box? It's the equivalent statement as the definition. It's just symbolic. So it just says the measure of angle CAB is equal to 1 radian if and only if the segment AC is congruent to the arc C or the arc length CB. So again, it's the same thing as the definition. It's just in geometry ease or whatever you might want to say. Okay. So again, we have 2 ways to measure an angle. We have degrees, and we have this other measurement, radians, that is a little bit more abstract. The way that I like to think about it, and I think the way that's the most useful way to think about it, is trying to relate the arc length to this measure radian. So in our definition, it says that that central angle, 1 radian, or that central angle is 180 radian if and only if the radius is the same length as the arc it intercepts. Everybody okay with that idea? So what radius makes the measure of angle CAB equal to the measure for the arc CB? Anybody got an idea there? So what length for the radius should I choose for that arc length and that angle measure to be the same? Well, if AC is 1 radian, that also means that CB is 1 radian, right? So the central angle, which was also 1 radian, is now the same as the arc length. Everybody okay with that idea? So what I found that is, if the radius is equal to 1 radian, that arc length is equal to the central angle measure. That's the takeaway there. Now my goal in using this is going to be to try to create a conversion factor between degrees and radians. If we have these two different units of measurement for an angle, we'd surely like to be able to convert back and forth between these two different measurements, right? If you have miles and you have kilometers, you want to have a way to convert back and forth. Or if you have kilograms and pounds, you want to have a way to convert back and forth. Everybody's okay with that? Okay. Oops. So finding a conversion factor between degrees and radians. So let's say we have our circle, and just like we pointed out from before, I'm going to choose that the radius of this circle is 1 radian, so that the arc length and our central angle will be the same. Everybody okay with that? What size central angle do you suppose I want to use here? In a circle, what central angle is it going to be easy for us to compute the arc length for? Yeah. How about we use a 180-degree angle? Everybody okay with that? If I do that, what is the arc length for CB? It's the circumference of the circle divided by 2. Everybody okay with that? because it's just splitting the circle in half. What's up? What was the question? We're trying to get a conversion factor between radians and degrees. So this central angle splits the circle, right? That's why it's the arc length CB is going to be the circumference of the circle divided by 2. Did I answer your question, Josh? Okay. Everybody's okay there? And the circumference of a circle, does anybody remember that formula? It's 2 pi r, and since we're only have half of the circumference, we'll divide that by 2. So that's pi r, right? And what is the radius? One radian. So we can say that 180 degrees then is equivalent to pi radians. That's our conversion factor that we're going to use. That's important. That's something that you'll want to remember. You'll use it in the homework, and you'll use it a lot in terms of converting back and forth between degrees and radians in this course. Most students often find things easier to think about in degrees, especially at the start of the course. So being able to convert an unfamiliar situation to something that feels a little bit more familiar is often very helpful for us. So let's practice doing this conversion a little bit, okay? So let's do a couple of examples. So let's say we want to convert 152 degrees to radians. The way I'm going to set this up would be very similar to a unit conversion that you would do in like your chemistry class or your science class. I think a lot of us being juniors or better have had some chemistry at some point and probably done a fair bit of unit conversion. So that's the same idea that I'm going to use here. So I'm going to start with my known quantity, and I'm going to multiply it by a ratio. Now that ratio is going to be built from the conversion factor. If degrees are in the numerator, where do degrees need to go in my conversion factor here? In the denominator. So I'm going to have 180 degrees here. And the numerator then should be pi radians. Everybody's okay there? This should look a little bit familiar if you've had a chemistry course or even done unit conversion in any science course. I don't know what you do in biology or geology or physics. I assume you do a little bit of this somewhere. I know you do a lot of it in chemistry. I remember that from when I did chemistries. Okay, so the unit of degrees cancels out. And we have like the fraction 152 over 180 times pi radians. Now, in a course like this, more often than not, when we talk about an answer in radians, we'd want to express it in exact terms. So we'd want to express it as some fraction of pi. So I would want to reduce 152 over 180 to its lowest terms. Now you could do that by hand. It's not difficult to do by hand, but it's maybe a little tedious. The calculator can handle this for us. Some of us probably already know how to use the calculator to get it to do this, but I'm going to go through and show you guys in case you forgot, or you never knew in the first place. If my calculator app wants to open, sometimes it just really, come on, you silly thing. There it goes. So I can turn this into a fraction or a reduced fraction if I do 152 divided by 180. And then I pick the math command or the math button menu and choose the fraction command and press enter. It'll give me the reduced version of that fraction. That's nice to know, especially if you have to potentially take like an ACT or SAT this year. I don't know if colleges sounds like they're not really requiring those anymore, but maybe some of us want to do it anyways. So our exact answer could be 38 over 45 pi. Or we could have the decimal approximation by taking 38 out, divide by 45, and just multiplying by pi, which will give us approximately 2.653. I guess we should probably write radians at the end of this for right now. Eventually, we'll stop writing radians at the end of these things because anything with a pi in it will know that from context is talking about an angle measure in radians. But for right now, I'll try to be conscious to make sure I'm writing pi's after it. Delaney? So this is all I needed to do to reduce the fraction is this line right here. So this fraction command I get from the math button, and then it's the first option. You see it? So that's all you need to type to reduce the fraction. Did it work? Good. Everybody happy with happy with that? So in general, we'd prefer the exact answer, the one with the pi in it, as opposed to the decimal approximation, unless you're asked for specifically the decimal approximation. I would prefer to just give me the fraction in terms of pi. Okay? Let's go the other direction. So let's say we want to convert 2 pi over 5 radians to degrees. Well, just like the part with my amount in radians, and I'll multiply it by my conversion factor. Where should the pi go in my conversion factor, the numerator or denominator? Denominator. So those cancel out, the pi's cancel out, and I'm just left with 2/5 times 180 degrees. So when I do that, I think I get 72. Yeah. Is everybody okay there? Okay. Do we feel pretty comfortable converting back and forth between these? It's a pretty straightforward calculation. Delaney? 2/5 times 180. Oh. That's okay. Again, if I did something and it was a little too quick or whatever, certainly raise your hand and ask. I'm happy to re-explain it, especially in a case like that where it's like an, oh yeah, of course, that's what you did. You know, like that was nothing. No big deal. Okay. So another definition. So let's say we have a central angle. We'll say that this is theta. And we'll say our theta is measured in degrees. Or I'm sorry, in radians. In a circle with radius r, then the length of the intercepted arc S is given by S equal to pi r, or theta r, excuse me. If instead we had degrees, I'm going to have pi r theta over 180 degrees. So I gave two different versions of this definition. One where the angle is in radians, that's the stuff in black, and one where the measure of the theta is in degrees, that's the stuff in red. Rather than rewriting that up a whole definition, I just changed the one word that I need to change and then wrote it in red. Is everybody okay with that? Now, compare those two formulas. Does that make sense? How do I transform an angle from radians to degrees? I would multiply it by pi over, or I'm sorry, 180 over pi, right? That's all we've really done here to change the formula, right? So in this case, I have an angle in degrees. To turn it into radians, I multiplied it by pi over 180. That's all it is. It's the same formula. It's just got that extra conversion factor in it, stuck in it. And some of us might recognize this formula from geometry. I think this was a formula you guys used in geometry to calculate arc lengths. Does that look familiar? Maybe. I know it was a long time ago. Maybe it doesn't look familiar. It was a long time ago. I get it. But that was the formula used in geometry to calculate the arc length of a circle. Let's do an example. Sound good? Just practice using these formulas. Okay. Which version of the formula above is the one that we want to use, the black version or the red version? The black version. How did you know that? Because the angle is measured in radians. Very good. And so now all I need to do is plug things in. And if you type that into your calculator, I have 1.372 meters. How did I know the unit was in meters? Because my radius was also in meters. So the unit should match. Pretty tough, right, guys? Whoa, I had to plug stuff into a formula. It's totally hard. It gets harder. Enjoy this part. What if the radius is 3.8 inches and theta is 40 degrees? Which formula should I use now? Yeah, the red one. When I do that, I get approximately 2.653 inches. Why is this one an approximate solution and the other one I gave you an exact solution? Ben? Perfect. Yes, exactly right. So here, in the degree version, we're multiplying by pi. If that pi doesn't cancel out, you got an infinite decimal going on. There's no way you can write that all down. We got to round it off at some place. The previous one, you had two finite length decimals. So if you multiply those together, you're going to get another finite length answer. So I did that. I could list all the decimals without having to round anything at all. Is everybody okay there? And if I gave you like the arc length and the angle measure and asked you to find like the radius, you'd be able to do that, right? It's just a little bit of like extra algebra stuff to rearrange your equation or whatever, but that should be pretty easy. Okay. So section 2. So here we're going to talk about trigonometric functions of acute angles. This is your geometry class from a couple years ago. But we're not going to take anything for granted that you remember this. We'll restate everything that you need to know. So when we defined our trig functions in geometry, we did them for right triangles. And I'm going to call this angle here theta. So let's name the vertices here, A, B, and C. So using the angle theta that I've drawn in here, we need to indicate the sides that are opposite, adjacent, and hypotenuse, right? Relative to this angle theta, which side is the opposite side? CB or BC is correct. It's the side that is not part of the angle formed by theta. Which side is adjacent? BA or AB. That's the side that makes up part of the angle that is not the longest side. And then obviously we all know the hypotenuse is the longest side of the triangle. Keep in mind that if I chose the other angle to be theta, opposite and adjacent would have switched, right? Everybody's okay with that? You guys remember that from way back when? Okay. So in your geometry class, you surely define sine, cosine, and tangent in terms of a ratio of side lengths in a right triangle. For sine, we say it is equal to opposite over hypotenuse. Cosine is adjacent over hypotenuse. And tangent is opposite over adjacent. You might have used the mnemonic device SOHCAHTOA to help you remember that. So again, what that stood for is sine is opposite over hypotenuse. Cosine is adjacent over hypotenuse. And tangent is opposite over adjacent. Does this seem incomplete to you guys? It always seemed incomplete to me as a high school student. Because why isn't there, I mean, the ratios that we've defined here seem rather arbitrary. Why opposite over hypotenuse and why not hypotenuse over opposite? Right? Why not? Well, it turns out there are 3 other trig functions that you probably didn't talk about in your geometry class. There's cosecant, which is hypotenuse over opposite. There is secant, which is hypotenuse over adjacent. And there's cotangent, which is adjacent over opposite. Maybe we'll write out the whole word here too, since I'm guessing this may have been the first time many of us have seen these 3 trig functions. Dan? CSC. Yep. Again, if you can't read my messy penmanship, feel free to ask about it. I know that, especially by the end of the day, it gets kind of dicey. So the symbols are important in math, right? Particularly when it comes to not just the spelling of something, but like the symbols involved with a function. Like the letters matter, so I'm glad to repeat or clarify or whatever if we're not sure. So these 3 trig functions, cosecant, secant, and cotangent, are often called the reciprocal functions because they are literally the reciprocals of sine, cosine, and tangent, respectively. You remember what the word reciprocal means? Where you're just flipping the fraction? Let's do an example where we practice using these. Okay, so let's look at this example. We're asked to find the exact values of all 6 trig ratios for theta in the right triangle below. So those 6 ratios, we're going to have sine, cosine, and sine was opposite over hypotenuse. Cosine was adjacent over hypotenuse. Tangent opposite over adjacent. And then we're also going to find cosecant theta, which was hypotenuse over opposite. Secant theta, which was hypotenuse over adjacent. and cotangent, which was adjacent over opposite. So we're going to just fill in the values for these. But if I look at my triangle, it appears that something's missing, right? What am I missing? The hypotenuse. How would I have to find that? The Pythagorean theorem, a squared plus b squared is equal to c squared, where c squared is the hypotenuse. So plus 4 squared is equal to c squared. So c squared is 29. So c is the square root of 29. Is everybody okay there? Since we asked for exact values, I'm not going to actually find the decimal for the square root of 29. Is everybody okay? Delaney? Yes, thank you. That probably makes a lot more sense. The end result was still correct. I just got going too fast, right? Okay. So who can tell me what the ratio is for sine? 5 over the square root of 29. But do we really, are we going to leave our answer in this form? No, what was wrong with this form? Yeah, we have a square root in the denominator, which we don't like to leave our final answer that way. So what we do is we multiply the top and bottom by the square root of 29. That's called rationalizing the denominator. I heard somebody mumble, which is excellent that you remember that term. So I have 5 square root 29 over 29. Everybody okay there? Cool. Who can tell me what cosine theta is? Two square root 29 over 29. Bonus points for rationalizing your denominator before I even had to ask. Hi, school bus. It's the downside of leaving the windows open. Tangent. What's that one going to be? 5 over 2. Okay. Now, cosecant. What's that going to be? Square root of 29 over 5. And secant? Square root of 22 over 5. How's everybody feel on that? Pretty straightforward? Just using our definitions that we stated just a moment ago. Okay. Let's do another. Let theta be an acute angle for a right triangle. If sine of theta is equal to 1/3, find the values of the other 5 ratios for theta. So I'm going to start by drawing a picture. So here's my right triangle. And I'll pick that one to be my angle theta. It doesn't really matter which one you call theta, provided that you adjust the location of your side lengths accordingly. Everybody's okay so far? What piece of information haven't I used yet? That sine theta is equal to 1/3, right? What is that going to allow me to say? So if this is side A, B, and C, what's the side length for, or tell me one of the side lengths. Ben? Good. So Ben knows that sine is opposite over hypotenuse, so the opposite side needs to be 1, and consequently the hypotenuse, or AC, needs to be 3. Everybody's okay there? Okay. How are we going to find that third side length? What do we have to be careful about here, though? Yeah, so notice here that we're given the hypotenuse. So if I square root both sides and then simplify my radical, I have 2√2. Yes. Yes. Everybody's okay to hear? We're good with how to simplify the radicals? Okay. So now all I have to do is write down the values for cosine, tangent, cosecant, secant, and cotangent of theta. So cosine is adjacent over hypotenuse. Tangent is opposite over adjacent, but I don't like to leave my answer with the radical in the denominator. Cosecant is the reciprocal, but again, don't like to leave the radical in our denominator. Oh my goodness. Secant, I said was the reciprocal. I just put it in the wrong spot. You ever make a mistake? That happened to me. What do I have here? 3√2. Okay. Cosecant is the reciprocal of sine. Gee, golly willikers. Or you could have used opposite over, or I'm sorry, hypotenuse over opposite. You could have done that still too. And then here, again, if I rationalize my denominator, I get this, but really that reduces down to just 2√2. How do we feel there? Is that okay still? Still not bad, right? We're still basically just using those definitions. Here's a throwback to geometry question. Find the sine of 30 degrees without a calculator. Do you remember how to do this? Or do you remember what you did to do this? So we're going to need to remember our special right triangle. So for a 30, 60, 90 triangle, I don't know why I wrote those. That doesn't make a lot of sense. That's the bigger angle. The ratio of side lengths is x, x root 3, and 2x. So sine of 30 degrees would be x over 2x, which reduces down to 1/2. So that's the 30, 60, 90 triangle. We need to remember that. There's another one, though. What was the other special right triangle? There was the 45, 45, 90. Whose side lengths are x, x, and then the hypotenuse is x root 2. So this is just an aside, but you should remember those two special right triangles. They will be extraordinarily helpful as we go forward. So spending a few minutes and memorizing those, as I think you probably had to back in your geometry class. I do not fault you at all for forgetting between now and then, because it was a long time ago and they were not worth being a hill of beans last year in your Algebra 3-4 class. They will be quite useful here. So you should reacquaint yourself with those and brush up on those ratios. Okay. How do we compute sine of, say, 17 degrees? How would I do something like that? Anybody with an idea how we do that? How did you do it in geometry class? Use your calculator. That's the right answer. What do you have to be careful about before you start punching numbers in your calculator? The mode of your calculator is important. What mode should we do to do sine of 17 degrees? Degree mode. So you'll want to press the mode button right there next to the second and make sure that the degree is highlighted. If it's not, move your little cursor over till it's on the degree and press enter. To exit out of the menu, you press second in mode. So sine of 17 would be 0.292 and change. What if I wanted secant of 78 degrees? Do I have a secant button on my calculator? No. What do I do then? I don't use inverse cosine. You're close though. I'm going to do cosine and then take the reciprocal. So the notation looks very similar to inverse cosine, right? Inverse cosine is cosine -1 of something. If you try to do cosine inverse of 78, you're going to get an error. But we can do the reciprocal of cosine of 78, which is what we're doing here. So 0.41, I'm sorry, 4810. So just to show you again, if I did cosine inverse of 78, not the same thing. If I do that, I get an error. So you got to be careful about what it is you're doing there, that cosine inverse and the reciprocal of cosine are not the same thing. Everybody's okay there. So what I did was I pressed the cosine 78, and then this button that's right underneath the math button is the -1 exponent. That just makes the reciprocal. Okay. So a little calculator action. Here's your most common geometry problem when you guys were in the trigonometry unit. So when the direction says solve the triangle, what does that mean? Find all the side lengths and all the angle measures, right? Okay, so what can we find here straight away? The other angle, great. How do I find that? Okay, 90 minus the other acute angle, or you could have done 180 minus 90 minus the other angle. It's equivalent to doing the same thing. So here we have x is 49. Great. How are we going to find the other side lengths? Let's say we want to find this side length here. I'll call it y. We're going to use one of our trig functions. Which trig function would I want to use here? Well, first thing we should do is specify an angle. For the sake of argument, let's use angle 41. Okay? We know something about the adjacent side, and we're looking for the opposite side. So what trig function involves opposite and adjacent? Tangent, or you could have used cotangent. Either would be okay. So tangent is opposite over adjacent. And if I cross multiply, I get that y is equal to 12 times tangent of 41. So I type that into my calculator. And I get about 10.431. Okay. What should we use to solve for z? I would say there's a better answer than that. You could use that. Is that going to give you the most accurate result you can? Yeah, let's use cosine or secant. Because again, if we use angle 47, we know the adjacent exactly, and we're looking for the hypotenuse. So the advantage of doing this with cosine or secant, either one would be fine, is that we have no rounded answers in this equation. If we use the Pythagorean theorem or one of the other trig functions, we're going to have to use another rounded answer, and then we're going to round again at the end. So it's like we're double rounding when we don't need to. This way of going about it. The only rounding we're doing is at the very end of the problem. It's a slightly superior method. Now, for what we're doing, does it matter a whole lot? Probably not. But if you're like working at NASA and trying to land an astronaut on the moon, if you're off by like a few on the 1,000th place, you could miss the moon. So like somebody cares about being this particular and accurate. I don't know what you're planning on doing with your life, but we're going to act as if you might someday have to land somebody on the moon. So we're going to try to be as precise as we can in choosing how to set up one of these problems. And only round around the minimum number of times. Jesse, I want to make clear, though, that what you said was not incorrect. It is absolutely still a reasonable way of going about doing this. It just wasn't, in this case, particularly the best way. And as soon as I indicated what would be a little bit better, I'm sure you saw exactly why it was going to be a little bit better. Although in the, I don't know how many decimal places we'd have to go to before we found answers that disagreed. It's probably, 4 or 5 where, what, 4? Ben did it, so he says 4. I trust him. Okay with that, everybody? We remember doing these trig problems from geometry-ish? At least after we've done one of them, they kind of start coming back, I hope. Yeah? You guys are talkative today. Man. Zip it. Okay. So, last thing we'll talk about today is this idea of an angle of rotation. So up until this point, we couldn't define angles or any angle that was more than 360 degrees, right? And in fact, we really didn't even bother to define angles that were bigger than 180 degrees, right? If you think back to your geometry class, we didn't really ever measure angles this way, right? We really only thought about them going that way, where the smaller of the two angles was always the measure that we gave. Is that okay with you guys? You guys kind of remember that from geometry? We're going to invent a new way of kind of measuring an angle so that we can start talking about angles that, like 450 degrees or 10,036 degrees or negative 14 degrees. All of these angle measures that previously would have made no sense to us at all. So the idea here is we're going to embed our angle in the xy axis. So one arm of our angle that we're going to call the initial side is going to be fixed to the positive x-axis. And the other arm of our angle that we're going to call the terminal side, we're going to allow to pivot at the origin. So for example, if I wanted to draw a (310-degree) angle, I'm going to have my initial side, and then I'm going to rotate 310 degrees about the origin. So here's 90, 180, 270, and about 40 more. I'm just estimating. And that's our 310-degree angle. We're always going to be rotating for a positive angle counterclockwise, so going to the left. What if we wanted to do 670 degrees? Well, we start the same way. Our initial side is on the positive x-axis. So 90, 180, 270, 360, 450, 540, 630, and then 40 more is right here. What do you notice about these two angles here? If you just look at the pictures. Notice the initial side and the terminal side are in the exact same location, right? That this little spot here is 40 degrees and that's 50 degrees in both drawings. We have a name for these kind of angles. They're called coterminal. So they have different measurements. But the same initial and terminal sides. So if I ask you for an angle that's coterminal to 50 degrees, what can you do? Add 360. Yes? What if I wanted an angle that was coterminal to that one? Add 360. What if I wanted another coterminal angle? What could I do? Add 360 again. Is there any limit to this? No, right? I can keep adding 360 and adding 360 and adding 360. And I'm going to keep getting coterminal angles, coterminal angles, coterminal angles. Is there anything magic about the act of addition? Could I have subtracted? Yes. But what does a negative angle mean? Well, if I take my initial side and I want negative 310, instead of rotating counterclockwise, I will just rotate clockwise. So 90, 180, 270, and 40 more puts me here. So that's like negative 310 degrees. Which you'll notice is exactly the same as positive 50 degrees, right? Same location of the terminal side. This is a super, super important concept. It's one of those that, like, if you don't get comfortable with this idea of coterminal and being able to draw these angles, life gets very difficult very quickly. So this seems like kind of a silly skill and a silly thing, It is not. This is really a kind of a critically important idea, because what you're basically doing is finding angles that are equivalent to one another, right? Can you simplify this angle into something that's easier numerically to deal with, rather than taking the cosine of 770? I can just do the cosine of 50 because they're coterminal, right? That's the power. So why don't you just, we have a few minutes left. I'm not going to go any further. I just want to have us do a little bit of practice here together. So just in your notebook or whatever you're kind of got handy, we're just going to scribble some drawings down. So I'm going to give you an angle to draw. Okay? We're going to give you a second to draw it. Then I'll draw it with you guys and talk about how we got there. Just to practice this a little bit right now before you go on, because I think this is a really underrated and pretty important skill. Okay? So let's say we're drawing we're drawing a 630 degree angle. So we have our initial side going counterclockwise, 90, 180, 270, 360, 450, 540, and then I'd be at 630 right there. Is everybody okay with what we did there? What if we instead did asked you to do 10 pi over 3 radians? Try to do it without converting it into degrees, which I know is your natural instinct to want to do. So if this is 0, 90, 180, 270, 360, what are those in radians? 0, pi over 2, pi, 3 pi over 2, 2 pi, etc. Try to do it in terms of, without having to convert the angle into radians. Maybe think about it as 3 1/3 pi's. Does that help? Right? 10/3 is the same as 3 1/3, right? So a half, 1, 1.5, 2, 2.5, 3, and like a third more. Now that wasn't easy probably for most of us. I made it look really easy because I've been being a math teacher for like 20 years. Okay, it's one of the added benefits is you get really good at these like high school math problems that were not easy when you were a high schooler, but you've done the same problems for 20 years. You get pretty good at it after a while. That should not have been easy probably for any of us to conceptualize in our head. It's a very different measurement system. You're dealing with fractions and pies, and it gets kind of confusing. That's okay. That's fine if that's where you're at. We should be able to get to the point where you can kind of count in radians, though. So again, the idea is we're going to count by halves. Each quadrant is a half a pi. Just take your fraction, convert it into like a whole number and a fraction, and you should know where that fraction lands in respect to halves, right? You know what I mean, guys? Does that make any sense, what I'm saying? And if you think about it that way, it's not too hard to count. But initially, you look at that and it's like, oh, I'll just convert it to degrees, which is fine, like it's effective, but you should be able to do that without having to convert it to degrees. Just FYI, on the homework set, you guys should be able to do up through 44 after today. I'm sorry, that's a lot. In fairness, some of them are just like literally plug it into your calculator or convert from radians to degrees or vice versa, which are like, I don't know, 30 seconds problem max maybe. So I think it's a lot of numbers, but it's really, some of them are quite easy. Anyways.